Hello, my name is Scott Grizzard. This is Calculus. This is Labor Day, the 7th. Of course, you're probably watching this Tuesday, which is tomorrow. But this is Labor Day, 2020. Calculus, as I said, I'm Scott Grizzard, University of South Florida. There's that. Um, Today, we're going to be talking about infinity and infinitesimals and limits at infinity. So last couple lectures, all of them, we've been talking about things in a very theoretical sort of theoretical kind of way. And we're going to be doing that. No, don't fear about that. But today we're going to be discussing something that is a little more practical. So today we're going to be talking about, let's see if I can make this work. There it is. This is now clipping my head. That's annoying. I can't fix that because I didn't iron the green sheet behind me. So I'll just lower the chair. Okay. So the last time we were talking about things like the definition of a polynomial, then how to write proofs and all of those things. And those are very important. Today we're going to skip a section. The book goes on to talk about continuity, which is very important. We'll talk about it on Thursday. But today what we want to focus on is computing limits at infinity. And there are some tricks that are very intuitive that correspond directly to how we want to approach, that correspond to kind of the intuition that we want to get for doing derivatives and doing limits at infinity and dealing with asymptotes. So that's what we're going to do today. So last time we talked about writing proofs. We did the definition of a polynomial, and we proved that polynomials have this thing called the direct substitution property, which, as you recall, simply says for if P is a polynomial, then for any a, the limit as x goes to a of p of x equals p of a, which meant we could just sub it in and find the thing. Oops, I've writing on Robinson then. There. And that's a very nice trick. Today, what we're going to be talking about is some other aspects, especially when we start taking limits to infinity. Okay? Now, so those are the things. And then, of course, we did some trig proofs. We'll come back to cool stuff like that. But what we want to focus on is kind of these other things that you can do with infinity. So first of all, we need to define it. What do we mean by infinity? There is a formal definition for this class. We'll just go. What we mean by infinity. In this class, we mean unbounded with direction. And here's that horrible word again. We mean arbitrarily large or arbitrarily small. Okay? Let's take an easy example. Are there any questions? 1 to 5, how do we feel about that concept? Just really, really big, or I'm sorry, not arbitrarily large. We mean arbitrarily positive or arbitrarily negative. So how do we feel about that? Okay. So we mean just really big. So for example, we're going to say that the limit as x goes to infinity of x squared equals infinity. As you go off into the direction of infinity on the x-axis, you go up to infinity on the the y-axis. Likewise, we're going to say the limit as x goes to negative infinity of x squared equals positive infinity, right? So if we take our old parabola friend, this thing's not going to like pop up my, okay. So if we take our old little parabola friend, fx squared, and we plot it in Desmos here, we're going to see that as we go up to 5, we go off to positive infinity. And then as we go to infinity, infinity, infinity here, as we get really, really big in this direction, we get really, really big in the y direction. Likewise, when we get really, really negative, when we get really, really big the other direction, we get really, really big in the up direction. So that's kind of what we mean. We also don't want some things. We want x squared times side of x to not have an infinity. So if I do x squared times sine of x, yeah. I don't want this to have a limit, right? This limit is not infinity because it keeps going around. So there's one sense that because it oscillates between, negative and positive infinity, and the same thing with tangent. So there's this sense that we don't want these things to have. Okay, so there's this sense that we don't want that to have a limit. Okay. Do a little. Okay. Let's just go ahead and snip this little bit in here. If I can, yes, I can. Okay. And there's our little friend, f of x equals x squared. Oops. All right. Okay. So we have this idea of what we mean by infinity. Well, let's build on that. Okay. And let's do a couple little let's make a little theorem about computations. Okay. First is the first of the nothing else matters proofs. The nothing else matters theorems, which make our lives easy, easy, easy. Okay. The first one is this. Suppose P from R to R is a polynomial. Okay? In particular, P of x equals C0 plus C1x plus C2x squared plus ... plus C n x to the n. Then the limit as x goes to infinity or negative infinity of p of x equals the limit as x goes to infinity of Cn x to the n. In other words, use the top term and nothing else matters. So this will be nothing else matters polynomial. We'll have another nothing else matters, and you can always use them for the same thing. So all this term thing says is that if I'm talking about a polynomial, okay, and I have a whole bunch of terms, who cares? The only term that matters is that Cn. Let me give you an example. Okay. The limit as x goes to infinity of, oh, and works for negative infinity too. Okay, the limit as x goes to infinity of x to the, of 10x to the fifth plus 1,000 x to the fourth minus 1 billion x to the third minus 10 equals, nothing else matters, the limit as x goes to infinity of 10 x to the fifth. Nothing else matters but that term. And when you think about this, this makes sense, right? Because if I have x cubed up here, let's go ahead and go back to our little Desmos, right? If I have x cubed minus 100x squared, okay? Now, when we're talking about the stuff between 0 and 100, that 100x squared matters, right? It pulls us below the x-axis. But after 100, right, this x cubed term just drowns it, right? If I throw 1,000 into this thing, right, does that 100x cubed actually matter? A little. If I talk about, if I'm talking about, the money I have in my wallet and I tell you I have $100 plus or minus 50, that plus or minus term matters. That's an important thing, right? That's the difference between 3 coffees at Starbucks and 1 coffee at Starbucks, right? Or something like that. But if I tell you that that the national debt of the United States is some trillion plus or minus $100, you're going to go, so what about I don't care about the $100, right? We're talking the national debt. And so, scale matters in a sense. And the point is that whatever this top term is going to dominate the conversation. How do we feel about that, 1 to 5? If we're talking about a polynomial, it doesn't matter. Okay. Let's see here. Here's another example. The limit is of x to the 7th minus 1000 x to the 6th. The only thing that's going to matter is this x to the 7th term. And x at 7 is odd, so x to the 7th is headed to the basement as you go to the left. It's supposed to be a 7. All right, so that's the first thing. Just kind of nothing else matters. Okay. And intuitively, it's obvious, right? Well, maybe not obvious, but once you state it, it's kind of like, oh, okay. All right. I should say I'm not going to do the proof. I'm going to skip this proof. This fact is kind of intuitive. I'll prove the next one. Oops. I did not know I had selected you. Okay. And now it's got to pop up the... I hate the way it does that. I wish there was a way to stop it from doing that. There probably is. I just haven't figured it out. Okay. Well, that's nice. Let's see how we can apply this to some other things. And this is very quick, right? I don't have to compute any of this thing. I don't have to take a fraction or anything about this. Yeah, we can prove it real fast. Stop it. The proof is actually simple. It depends kind of on the definition of a rational function. So let's do that first. Stop. Okay. So we're going to do this function f. So let d be, let all right, we'll just do this. F is a rational function if there exist polynomials P and Q, Q not the 0 function, so that for all x in D, f of x equals P of x over Q of x. Okay, so this is a rational function. Okay, can someone give me an example of one of these? It's a ratio of two polynomials, right? So examples. X cubed over x plus 2. X over x squared minus 1. 1 over x. The polynomial x, or just x squared. These are all rational functions. How do we feel about that? I just take one polynomial and I set it over another. And my hands are very clipped tonight because I need to iron my green screen. So I need to watch that because if I don't crop it, it doesn't work. Okay. So x cubed is a polynomial. X plus 2 is a polynomial. So this is a ratio. So this is one polynomial over another polynomial. This is one polynomial over another polynomial. This one happens to be a monomial, but that's still a polynomial. This right here is a constant over x. This is x squared over 1. So, of course, x squared is in there too. Okay. Now, there are a couple things that we can apply about polynomials, about rational functions. First, there. Note that these things only work for infinities right now, right? NEM only works for infinity. Nothing else matters, only works for infinities. And you are taking an infinite limit, then only the lead terms matter. Okay? Example. The limit as x goes to infinity of x cubed minus 5x squared plus 3 over 2 minus x to the 4th plus x cubed. I take the top terms. So the top terms here are x cubed and negative x to the 4th equals the limit, and this is NEM, nothing else matters. The limit as x goes to infinity, these are the two terms with the biggest exponents, x cubed over negative x to the 4th equals the limit as x goes to infinity. I'm going to do a little cancellation here. And I get 1 over negative x equals 0. All right. So how do we feel about that little trick now? If I've got something rational and I'm going to something infinite, I can just get rid of everything except those lead terms. Oops, nope, wrong thing. Okay. Let's do one more, because this is actually kind of interesting, because you can wind up with finite things when you do this too. So let's say I've got 5x to the 8th minus x squared plus 1 over 3x to the 7th minus 2x to the 8th plus 16x squared. Who cares? Nothing else matters because I'm doing an infinity. Now, it's important that I can only do this when I'm doing infinities. 5x to the 8th, right? That's my top term, and that's my top term. Over negative 2x to the 8th. The 2x to the 8s are going to cancel, and I'm going to wind up with the limit as x goes to infinity of 5 over negative 2, which equals negative 5 over 2. Right? Because this is the limit of a constant. So this is a very, very, very useful theorem. You just go, you don't have to sit there, you don't have to factor things. WebAssign wants you to divide by the highest term out over those, and that's actually how you prove it. But you don't need to do that. You just take biggest exponent on the top, biggest exponent on the bottom. You divide one by the other. You're going to go infinity, 0, or you're going to do something like this, where you wind up canceling the two x terms, and you wind up with 5 over negative 2. And this is very simple application of the fact that as you go up, the biggest term is going to dominate everything. Okay, well, that's the first kind of useful little fact. Are there any questions, by the way? Okay. All right. Theorem. If f is a rational function and a is in the domain of f, in other words, does everyone feel okay with that statement? If f is a rational function and a is in its domain. For example, 2, why is it not negative infinity? It was negative infinity. Oh, why is it? Because I'm going to negative infinity on x cubed, right? And if you remember from pre-calc, or if you don't remember from pre-calc, x cubed goes kind of like this. So it's a good question. Don't feel stupid. You just didn't remember from pre-calc, which is okay. We can go over it. So here's what x cubed looks like. Remember, it kind of does this thing where it just kind of goes down to negative. As it goes to negative infinity, it just heads for the basement. Okay. Does that answer your question? Right. My x is heading to negative infinity. Therefore, my y goes to negative infinity for x cubed. Good question. Okay. How do we feel about this? If f is a rational function and a is in the domain. So what I'm talking about is that if it's p over q, q of a does not equal 0, right? It's defined at this number. Okay. Then the limit as x goes to a of f of a equals, f of x equals f of a. In other words, rational functions have the direct substitution property on their domains. All right, so let's do an example of that. The abbreviation, by the way, for this theorem is dsrat. All right, let's do an example. Let's let f of x equal, let's do something on the bottom that's easy, x. Now let's do something on the top like x cubed minus 5. Then the limit as x goes to 1 of x cubed minus 5 over x equals 1 cubed minus 5 over 1. Because the bottom is not 0, right? If I just take this 1 here and sub it in, I get something on the bottom that's defined. I'm perfectly happy with that, right? Oh, well, 1 cubed minus 5 is negative 4. And that's it. I don't have to factor. I don't have to divide. I don't have to do anything crazy. I just go, okay. And I just sub it in. Do another one. G of x equals x squared plus 1 over x plus 1. The limit as x goes to 1 of x squared plus 1 over x plus 1 is what? Well, where is this thing not defined? Where am I in trouble in this function? Is it at x plus 1? Is it positive 1? No. Positive 1's fine, right? It's negative 1 that this thing's not defined at. If this was negative 1, I'd be in trouble, but this isn't. This is positive 1. I can deal with that, right? I just go, oh, okay, equals 1 squared ds rat. I should put that over both of these. Direct substitution on a rational function, or just ds. 1 squared plus 1 over 1 plus 1 equals 2 over 2 equals 1. Well, that was easy. Easy button, that one. How do we feel about this 1 to 5? As long as I'm in the domain, I'm good. Okay. Of course, now how do we deal with a's that are outside the domain in rational functions? And this is kind of the meat. Okay. We've dealt with concepts of infinity. We've dealt with nothing else matters for polynomials. We've dealt with the rational functions. We did nothing else matters here. So this is nothing else matters. This is ds rat. This was ds poly, by the way. No one actually writes the poly bit, but you do write ds. And this right here is nothing else matters. Polynomial addition. Okay. That's right. And don't you forget it. That's right. Nothing else matters but Scott's calculus class. Usually, what I do here is in class is I, play the Metallica song, but of course the Metallica song is copyrighted, and we're on the internet now. So I can't do that. All right. So the question is, how do we deal with A's that are outside the domain? How do we figure those? All right, so there are a couple tactics. The first thing I can do is I can factor it. Okay. So, tactics. Can you factor? And this is actually going to be the last thing I try, but it's going to be the first thing I talk about. And I'll get to why in a moment. So, let's do an example here. Let's do the limit as x goes to 2 of x squared minus 4 with x plus 2 on the top. Well, let's put x minus 2 on the top. Just for the first one. We'll do x plus 2 in a moment. All right, well, I can't sub in 2, right? No direct sub. Actually, more importantly than the bottom just being 0 is the fact that you'd wind up with 0 over 0. I can't direct sub because the bottom would be 0. So what can I do? Well, I can factor this, right? The limit as x goes to 2 of x minus 2 over x squared plus 4 equals, well, x squared plus 4 is the same thing as difference of squares, x plus 2, x minus 2. And by the way, that difference of squares trick, you're going to want it because you can actually do it in more places than you think you can. You can actually do that in a whole bunch of very cool places. So I've got x minus 2 over that. I cancel the two things on top and bottom. And I wind up with the limit. Oops, there should be a limit sign here. Laura needs to take 2 points off my quiz right there. I forgot my limit. Limit x goes to 2 of 1 over x plus 2. It's very important that you carry through those limits. And then I can direct sub, and I wind up with 1 over 2 plus 2, which equals 1/4. How do we feel about that, 1 to 5? Okay. Crickets? Okay. All right, so that's kind of the classic way to do this. That's the way WebAssign's been having you do it. But let me show you what I mean by this difference of squares thing being very powerful. Let's say I want to do this. The limit as x goes to square root of 2 do I want to do that? No, I want to do the x goes to 2 of x squared minus 2 on the bottom. No. X minus 2 on the bottom, and square root of x minus square root of 2 on the top. Oh, this should be, by the way, a minus there. All right. Well, how am I going to get at this? And the WebAssign answer is that you multiply by the, you multiply both the top and the bottom by the square root of x minus the square root of 2. But this is actually a difference of squares. Well, what squared is x? Well, the square root of x squared is x, right? So this is actually the square root of x minus the square root of 2 times the square root of x plus the square root of 2. And the giveaway is this thing on top. So you can actually factor these without, doing the what is it called again? I can never remember because I almost never do it. Instead of multiplying by the conjugate, there it is, got it. So instead of multiplying by the conjugate, I can also get at this by factoring the bottom. And now, since 2 is in here, I just directly substitute in, and I wind up with 1 over the square root of 2 plus the square root of 2, which equals 1 over 2 root 2. How do we feel about that, 1 to 5? So the point is that this whole multiply by the conjugate thing, which you can do, is often superfluous. You can factor things that you didn't know you could factor, which is actually kind of powerful because it will save you huge amounts of time, right? You've got a lot less multiplication going on here, a lot less room to make mistakes. So, sometimes factoring is easier than multiplying by the conjugate. Okay, the next thing I can do is I can use an infinitesimal. And this should actually be the first thing that you do. Okay, so infinitesimals, doing this trick, one, it's legal on the test. Okay, the other classes may say no. For mine, it is. These things fall in and out of favor depending on your decade. But they are legal and they're really, really cool. So when Leibniz initially thought about derivatives, he thought of it as a ratio of two infinitely small amounts, which he called infinitesimals. But he called them in German. So, infinitesimal, right? Because he's speaking in German. Now, but it's, it's this idea of a little nudge on top and a little nudge on bottom. Okay? Just a little nudge on top and a little nudge on bottom. But yes, this is life. So, how can I do that? That's the thing. I want to think about the number that is just to the right. Let me give you an example. So, think of a minus as the number just to the left of a. Likewise, think of a right as the number just to the right of a. And always, always, always think of England, right? Think about 1 over x. All right? Now, here's what I mean by this. Let's go back to that example we had before. But let's change it a little bit. Let's do the limit as x goes to 2 of x minus, which one did I do? No, I did minus last time. So plus 2, x plus 2 over x squared minus 4. Now, I could factor this, but let me show you a better way to do this. Okay, well, I've got 2 things going on. I've got a 2. So think of 2 minus and 2 plus. Okay. Here's 2. Here's 2 minus, and here's 2 plus. Now, if I add 2 to 2 minus, where am I? I'm just to the left. So if I start just to the left of 2 and I add 2, I am now just to the left of 4. Likewise, if I was just to the right of 2 and added 2, I'd be just to the right of 4. So I have 2 minus plus 2, right, is 4 minus. And 2 plus plus 2, or 2 right plus 2. It's easier if you think of them as left and right. Don't think of them as plus and minus. Think of that thing as 2 left and 2 right. So 2 right plus 2 is 4 right. How do we feel about that, 1 to 5? And I cannot express this enough. Draw your number lines. Now, let's do it again, but let's do it for this x squared minus 4 bit. Okay? If I'm at 2 left and I square, where do I wind up? Two right squared, 2 left squared. Well, I'm just to the left of 2, right? Correct? And now I square, and I'm now to the left of 4. I'm a little bit farther away from 4, but I'm for all intents and purposes, just to the left of 4. Now, 2 right squared is going to be 4 right. Now, what am I going to do? I'm going to head back to 0, correct? So now I'm going to go subtract 4. I'm going to wind up at 0 left. And here I'm going to wind up at 0 right. Now, when you're around 0, remember that 0 left is a negative number, and 0 right is a positive number. Let me say that again. 0 left is a negative number, and 0 plus is a positive number. It doesn't get that from the 0 minus. It gets that from being on the left side of 0. Now, the limit as x goes to 2 from the left of x plus 2 over x squared minus 4 is the same thing, and I'm putting an equal sign here, but it's not, equals is a bad thing because I'm mixing two concepts. I'm mixing an infinitesimal with a limit, and that's actually technically illegal, but I don't really care because it's useful as hell. This right here to the left is going to be 4 left over 0 left. Now, as I said, always keep in mind about 1 over x. As I approach 0, what is this thing going to do? As the bottom goes to 0 left, and I don't care about the top is actually just 4 now. What is 4 over 0 left going to be? If I have 4 over x and I head to 0 from the left-hand side, what happens? As I head to 0 from the left-hand side, what happens? Bye-bye. So 4 over 0 left is negative infinity. The limit as x goes to 2 from the right, x plus 2 over x squared minus 4 equals, well, I had 4 right over 0 right, which is the same thing as 4 over 0 right, and that's going to head to positive infinity. So the limit does not exist. How do we feel about that 1 to 5? Okay. All right. Well, let's do another one. Let's do the limit as x goes to 0 of x squared plus 2 over x squared. Now, I can't use nothing else matters out here, right? I've got two things here. I'm going to use the exact same method. I'm going to consider the infinitesimals. So, if I take 0 left, now let's do x plus 2. Easier. So let's look at 0 left. Well, 0 left plus 2 is what? If I'm just to the left and I add 2, I'm going to be at 2 left. Now, and then 0 right, I'm not going to do this one. 0 right plus 2 equals 2 right. I think we can all get that. Now, what happens to 0 left when I square it? Remember that 0 left is to the left of 0. So if I square 0 left, I'm suddenly to the right of 0. I squared a negative number. How do we feel about that? 1 to 5. That 0 left squared is 0. I've squared a negative. And 0 right squared is also 0 right. So now what I have is that the limit as x goes to 0 right of x plus 2 over x squared equals-ish, because I'm mixing two concepts, which is fine. 2 right over 0 right, which is just 2 over 0 right. And that goes off to positive infinity, right? Because don't ever forget whenever x. But look at this. The limit as x goes to 0 left, x plus 2 over x squared, equals 2 left over 0 right. And that is also positive infinity. So this limit exists. This limit is infinity. How do you feel about that? 1 to 5. And note, I didn't have to factor anything. Here I couldn't have factored anything. But that's the important thing, is I don't have to factor anything. I can try this first. I can try, am I going to get now? When do you have to do more work? So, if you sub in, you'll get one of these forms, right? If you get a form, right? If you get a form of something, so if you get something like 2 over 0 plus, that's positive infinity. If you get something like negative 2 over 0 plus, that's negative infinity. If you get something like 0 plus over 2, that equals 0. If you get an infinity over 0 plus, that equals positive infinity. If you get infinity over 0 minus, that equals negative infinity. If you get 2 over 0 minus, that equals negative infinity. If you get 0 plus over 0 minus, more work. It's indeterminate. So if you get something like 0 plus over 0 minus, 0 minus over 0 minus, 0 minus over 0 plus, or 0 plus over 0 plus, you need more work. Okay, let's do an example of needs more work. Right, if I have, again, the limit as x goes to 2 of x minus 2 over x squared minus 4. Okay, and I sub in here. So let's say I try it here. I do, okay, so, and let's just do from the right. So I only have to do one of them. 2 plus minus 2 over, this is a 2, so 4 plus minus 4 equals 0 plus over 0 plus. Need more work. Right, 0 plus over 0 plus is indeterminate. You have to do more work. More work is needed. Are there any questions? So how do we feel about this trick, 1 to 5? Okay. I know I've watched the 5s go down to 4s, go down to 3s. You know. Okay. I'm telling you, if you play with this trick, just draw the little number lines, and this trick will save you so much heartache. Because it saves you all your factoring mistakes, as long as you don't wind up here. Here, I have to factor, right? Need more work. So here, I'm actually going to have to factor. Okay, so this is the same thing as the limit as x goes to. So this all, no good. This is going to become the limit as x goes to 2 from the right of x minus 2 over x minus 2, x plus 2. Cancel me, equals the limit as x goes to 2 from the right of 1 over x plus 2, which equals ds. Right, because now I'm in the domain 1 over 2 plus 2 equals 1 over 4. Okay, are there any questions, comments, issues, suggestions, or thoughts? Okay. If you have any questions, I'll be happy to help. The WebAssigns will work you through this. Again, the WebAssigns wants you to use different tricks for this. And that's okay. I mean, you can divide them through by the highest term. That's okay too. But it eats your time on tests. If you get good at this tactic, if you get good at these tactics, they save you time. Okay? And that's the point. What's the point? A few intuitive tricks. Can save you time. And, heaven forbid, help you with the intuition. Okay, So this evening, or today, if you're watching it now, of course, we went over. I didn't do any of the proofs. They're in the notes if you want to see them in various ways. I skipped all the proofs though. If you want to see them, they're in the notes. But I've been doing proofs and long things for a while now. I thought, just doing some tricks about computation should be. We should do it. By the way, the guy who finally formalized this was Robinson, and you can tell he lived in the 20th century. He's the guy who actually figured out you can do these things, in a very formal mathematical method. So that's where he comes in. He's also the guy. It's called non-standard analysis as opposed to French analysis. Okay, so we talked about the definition of a rational function, and we talked about things that we can compute quickly. Next time, we're going to talk about continuity in the intermediate value theorem. So that will be on Thursday. Are there any questions? All right. So that's it. Your quiz is the quiz for Wednesday is posted. It's 3 pages as opposed to the normal 2. I did that intentionally because I want to make sure that you can do the. I'm supposed to post this stupid little fake quiz and make sure that you can do multiple pages in the Gradescope. I break the quiz up into 3 pages instead of just 2, and it serves the same purpose. So to make sure that everyone's figured out how to do that, but it is up, it's posted, as is the problem set for this week. And I will see everybody on Wednesday. Thank you.